And I'm happy to introduce you the last speaker of this section. It is Alexander Teretenkov, Closed Dynamics of Moments and Operator Space Fragmentation for Quantum Dynamical Semigroups. Please welcome.
Thank you for introduction, and thank you very much for the organizers for the possibility to give a talk at this conference. I actually have participated all OPSO conferences, but I now realize that I never discussed this topic on them, despite I have it takes much my scientific time. So this is why I take this theme for this conference, and I will discuss several GKSL generators for which I will show that I have closed dynamics of moments or something like that. This is outline of my talk. I will discuss Poisson type generators, diffusion type generators. Then I will start with bosonic case. Then I come to fermionic case. I will discuss so-called Ansager space, and then depending on time, I will discuss the averaging of the quadratic generators. Well, the GKSL equation has been mentioned several times for this section by previous speakers, so this is just a reminder what we speak about. And first of all, I will consider this specific type of GKSL equation, which I call Poisson type generators. This is the case when the Limblad operators CK are proportional to unitary operators, and here we have no Hamiltonian terms. This type of generators have long history. It was discussed by Kosakovsky even before these GKSL papers, and then it was discussed by Kummer and Maassen, by Frigieri and Maassen, and for infinite dimensional case, it was discussed by Holevar in his papers by covariant quantum Markovian evolution, which is mostly this papers has most connection to the first part of my talk. And there are still some recent physical applications of this generators, for example, by Tubilka and Basharov, and by Linovsky, myself, and Dulgivsky. Well, I have to introduce some notation. I consider usual Gilbert space, which is the tensor product of copies of L2. I have usual creation and annihilation operators, which I compress in one vector with elements being creation and annihilation operators. Then canonical commutation relation have the following compact form. Jane's matrix of the symplectic form. I need the following notation that I call tithe conjugation, which is conjugation, element-wise complex conjugation and multiplication by this constant matrix E for vectors at left-hand side and for matrices on both hand sides. And based on this tithe conjugation lead me to define essentially self-adjoint operators, which are quadratic forms in the creation and annihilation operators. And then I can formulate the first theorem of my talk. If we have density matrix satisfying the GKSL equation with unitaries which have quadratic generators, then the dynamic and at initial state we have finite moments. Then the dynamics of the moments defined by matrix exponential of finite dimensional matrix, or you can write not the matrix exponential, but the system of ordinary differential equations which are linear and with time-independent coefficients. So the main point that the dynamics of the moments of the fixed order, here of the order of m, are preserved during the evolution. They are not coupled somehow for lower order moments or higher order moments. This is I mainly follow this my work in mathematical notes, and here's just simple first and second moments, just to write it this notation more explicitly. The similar thing can be done for so-called diffusion type generators, which are also occurs in the possibly not on by this term, but in the works by Hollow, which I mentioned before. They are. This is nothing else but the case when our limit operators CJ are essentially self-adjoint, and for this specific case they are quadratic forms in creation and annihilation operators. And once again we have closed dynamic of moments of the fixed order. So if we have the moments of the order m, they are transforms during the evolution only to the moments of the order m. So they have these properties. This property was discussed by Bartel and Zhang in this work, and by Ivanov and myself in the following work in math notes. Also, just for explicit view, we have this formula for first and second moments. If you have something for diffusion type terms and unit Poisson type terms, then you can write in principle something for the generators which occurs due to averaging with respect to Levy fields. Of course, I call this terms Poisson type or diffusion type, not by formal notation, but because they occurs due to averaging with respect to Poisson processes or Poisson fields in general, or due to averaging with respect to Wiener processes and their generalizations, multi-dimensional generalizations. And for example, you can also attack. You will have the similar properties if you consider the generators which occurs due to averaging with respect to Levy fields, because they are due to Levy-Hinchman theorem reduces to these elements which I discussed before. For example, not just for processes but for field systems, can be found in this book by Sato. But what I should mention that when for one scalar stochastic processes, such combinations, the possible generators can be characterized in terms of so-called Bernstein functions, which have well-developed theory. We have tables of specific examples, for example, in this book by Schilling-Zomb and von Dracek. But nevertheless, the fact that we have the whole books on these functions means that the fact that reduced doesn't mean that reduction is obvious in particular cases. So it's not very. I mean, for example, with book, without looking to the table, it's sometimes not very obvious that this specific generator is a Bernstein function of some quadratic generator, for example. But nevertheless, in principle, the Hitchin type theorems allows one to do it. What I should say next, that it is possible to generalize, of course, this story for the fermionic case. It's even more simple because it's finite dimensional. I mean, I consider both in bosonic case and fermionic case only finite number of modes. And for fermionic case, in this case, we have just finite dimensional operators. So it's in certain sense even more simple. I have the similar notation. I have Hilbert space of this c to the power of 2 to the power of n. It's well known that it's possible to realize a canonical anti-commutation relation in this space. And I also will compress all the notation in such a way that all these creation and annihilation operators are combined in one two-dimensional vector for these operators. Then canonical anti-commutation relation have the following form, where E is exactly the same matrix as before. It's 0, 1, 1, 0 is block diagonal, block of diagonal matrix. Then it's possible to do the same. In this case, I will, of course, it's possible consider both diffusion type generators and unitary Poisson type generators, but I will consider only Poisson type for the simplicity. And what is important, I will, of course, we have the same property that the moments of the creation and annihilation operators during the evolution map to the moments of the same order. But what is also important, of course, it also can be done for bosonic case, but I'm just follow the works I have written. So I consider it in the fermionic case that it is possible to calculate also Markovian multi-time ordered correlation functions in this case by in this similar sense, namely, well, this line is the definition of the Markovian multi-time correlation functions by so-called regression formula, and due to the fact that you can do something like similar to the Heisenberg representation here, you can act by adjoint evolution to these operators, constitutes this vector of creation and annihilation operators. Then it is easy to show that you can also calculate explicitly.
Spend a week just by watching.
Sorry?
Yeah, watching.
I'm sorry. I will reach them all.
So,
Question?
No. It was
Sorry.
Sorry.
But this supported that it's possible to calculate this dynamics explicitly. It's important from the practical physical point of view because correlation functions is measures in experiments typically, and what it can be calculated. It can be possibly a bit hard to understand notation, but the main idea is the following: that we also have just product of semigroups which are have linear dimension in this small n. Because I mean, of course, you can always calculate it just solving this equation and having a semigroup which acts, which will be can be considered as an operator in the or matrix in the space to which is exponential in this n small. But what is important that here all these operators are have linear dimension in n small, possibly high, and for higher and higher correlation functions, you of course you will need the higher dimension. But nevertheless, even in finite dimensional case, it is much easier to calculate this computationally easier these semigroups rather than directly calculate semigroup solving this equation. And here I am following this work by me and using aside. Here is some generalization of the story. It's not obviously now related to the previous part, but I will discuss how it's related. And this in this form, it has more direct, I say, more direct physical applications. It's more directly can be applied to some problems of quantum many-body physics. Well, now let us consider also the space which is a tensor product of C2. So it's n capital here should be the n small from the previous subsection. And one can define so-called Anzager strings of length greater or equal than 2. What is it? It's sigma alpha or sigma z is a Pauli matrices. The index below is the subscript means the tensor factor in which they act, and they start from sigma x or sigma y. Then it should be n-1 sigma z matrices in different sides, and then it ends with sigma x or sigma y as well. And it's for Anzager strings of length equal or greater than 2, and the Anzager strings of length 1 are defined just as sigma z acting on site j, or that is acting on the tensor factor in these tensor products, which is jth. Linear span of the Anzager strings forms so-called Anzager space. Then it is possible to prove the following theorem if we have this GKSL generator such that H is in the is an element from Anzager space, and CK, that is Lindblad operators, can first belong to the Anzager space, or two is a unitary operator with a generator from the Anzager space, or 3 has the following form, which is a linear combination with real coefficients of sigma x and sigma y, or 4 is a product of any number of operators or of the form 2 or 3. Then the semigroup adjoins semigroup, meaning, well, we have just finite dimensional case. We have the scalar product, Hilbert-Schmidt scalar product for matrices, and then we can consider, of course, adjoint operator with respect to this scalar product. And this adjoint evolution is nothing else but evolution in the Heisenberg representation, leaves the Anzager space invariant. It's actually could be considered as a generalization of the previous discussion for fermions, because actually the called Jordan-Wigner transformation transforms this Anzager space to the quadratic forms and forms of creation and annihilation operators, fermionic creation and annihilation operators. So the first and the second are nothing else but generalization, direct, nothing else but the terms from the previous previous discussion. But what is important that also we have these terms and the combination with these terms, which are not elements of the Anasager space, that can the action of these matrices on left and right hand sides can be thought as outer automorphisms of the Anasager space, meaning they are not elements of the Anasager space themselves. Nevertheless, they if we act by these operators in the GK by the dissipator of with such CK, we will have we will leave the Anasager space invariant. So it's generalization. It's generalization, and what is important? It is important for some real physical situation, because such the generators of the form free occurs very naturally in the weak coupling limit and high temperature approximation. So it's very natural things. And what is more important? That under the conditions of the above theorem, the adjoint semigroup leaves the linear span of anti-commutators of elements from Anasager space invariant as well. So if we not consider only elements of Anasager space, but consider only all possible anti-commutators and also consider linear span, it also will be invariant, and so on, and so on. Actually, and so on. And if we consider now these elements with their anti-commutators with Anasager space, we also have invariant spaces. So we have some infinite number. Oh, possible no, not infinite in thermodynamic limit, but we have exponentially many such invariant spaces with dimension being linear in n. So this is very similar to the situation which we have for moments, and similar phenomena for the Schrödinger equation, usually called Hilbert space fragmentation in many-body physics. So we have adapted the term operator space fragmentation. This work by me and Lichkovsky essentially is this is mainly his contributions here to this story. But what is important, this work have very not only this abstract results, but applications to some specific physical models, actually the dissipative XX models. And what is also interesting, that invariant spaces sum up to Jordan algebra generated by Anasager strings, but it does not span the whole space of operators. So in a certain sense, I usually think about this closeness of moments as a kind of integrability, but it's certain, what is important in this case, it could be not completed integrability, but some kind of partial integrability. But what is important, due to the actually its dimension is half of the one for the whole space. So we have, of course, sometimes we have some specific, typically called scars, some specific solutions of the many-body problems. But here we have, in certain sense, half our space are in certain sense integrable, informally speaking, of course. Mathematically strict story of the integrability in many-body cases are still very, very discussable. Well, it's possible to go further and to consider the general GKSL equation with quadratic generators, and what I will not much time to introduce notation here, so I just formulate the theorem informally. if you have also the now average of the evolution with quadratic generator, which is nothing else but quantum Gaussian channel here instead of just unitary maps, then you have the similar situation, but not exact one. I mean, before the moments, the dynamics for fixed moments was closed, but here the dynamics for moments up to some order. So for all orders up to order m is closed. So we have some not fragmentation, but some kind of hierarchization in this case. So it's very similar to the, for example, Boголюбов hierarchy structure and so on. And I think so it's in this works, and I think I have no time. My time is finished. So thank you for your attention.